The second solid design principle I'd like to talk about is the Liskov Substitution principle. A good design satisfies the rule that it's possible to replace objects of some superclass S with objects of any subclass of S without altering any of the provable properties of that program. That is to say, without breaking the program. The principle is named for Barbara Liskov, who originally called the idea strong behavioral subtyping. The idea is that the behavior of a subclass should be as correct as the behavior of the superclass. For example, if I needed to create several readers for several distinct file types, I can define them as subclasses of this abstract superclass. Note that the Liskov substitution principle doesn't specifically mention abstract classes. Since abstract classes don't do much, it's difficult to take the Liskov substitution principle literally. It's common to apply Liskov substitution to each concrete subclass that implements the abstraction. Each subclass of this abstract reader class must start with these methods and have the same general semantics. In this case, for example, the read method has no parameters and no return value, and it leverages the internal state of the class, using the source attribute and setting the samples attribute. This version is a subclass that works for CSV format files. I've provided an implementation of the read method that satisfies the simple rule of matching the parameters and return types. It's less obvious without a unit test, but this also matches the required behavior. It requires the source attribute to be set, and it sets the value of the samples attribute. Here's another subclass of the reader class. This works for new line delimited JSON files. Again, I've provided an implementation of the read method. This satisfies the trivial rule of matching the parameters and the return types, and a unit test would demonstrate it also matches the behavior required. The idea behind this design pattern is to create a reader object built from one of the subclasses of the abstract reader class, and the choice of which of the available subclasses can be based on, for example, command line arguments, or a configuration file, or, as shown here, the suffix of the path. When we're strict about Liskov substitution, this kind of design works out very, very nicely. Another common phrase for this is late binding. Contrast it with the idea of early binding, where a file parsing algorithm would be chosen when we write the code. Any change would require modifying the whole application, and modifications can have destructive ripples to other classes. Late binding means the file parsing algorithm is selected at runtime when the file name is presented to the application. The Liskov substitution principle suggests that a subclass shares the same interface as its superclass. The advantage of late binding is flexibility. Decisions are put off until the actual input file name is known. This design also fits the open-closed principle, something I'll talk about later. When the classes are the same, it's easy to tell that substitution is possible. For subclasses that add features, however, the substitution can be a little more complicated to detect. Python gives me a number of implementation choices, and I need to choose carefully among them. The Python language does not require a formal definition of an abstract superclass. And while it often makes sense to use the ABC module to define superclasses for abstractions, we have two alternatives. I like to call these informal subclassing. Because of Python's duck typing, it's not essential to have a single abstract superclass. Duck typing means the code doesn't have to follow a strict inheritance hierarchy. If you haven't heard the term duck typing before, it comes from this. When I see a bird that walks like a duck and swims like a duck and quacks like a duck, I call that bird a duck. If two Python objects have the same methods and attributes, well, then for all practical purposes in Python, they may as well be members of the same class. Python doesn't rely on the declared type, but on the presence of methods and attributes. Tools like MyPy will check to confirm that classes used interchangeably really do have common methods and attributes. Here are two variant reader class definitions. I've left out the bodies of the CSV reader and the ND-JSON reader, but I've defined the two separate classes and gave them a common type hint. A collaborating class can use the reader type, and tools like MyPy will confirm that either of the two implementations fulfill the requirements of the reader interface. What's important about using a type union is that it does not leverage inheritance. There's no code sharing among the classes. Done poorly, this can lead to copy-paste programming. I'm not a fan of copy-paste. I don't recommend this as a way to implement the Liskov substitution principle. Common code needs to be in shared functions or shared classes, even when there's no formal class hierarchy to manage the shared code. Another approach to Liskov substitution is to define a protocol type. In this example, I've used the typing protocol type definition to define what is an abstraction for the various kinds of readers. I can then implement classes that fulfill the contract of this protocol. This formalizes Python's duck typing, and it can be easily checked by tools like MyPy. The protocol isn't technically a superclass, it's a description for tools like MyPy to use. It formalizes a contract for alternative implementations. It makes duck typing subject to static analysis, and it's ideal for situations where there's minimal shared code among the implementations. We can use type hints as one way to claim that several classes are supposed to be Liskov substitutions for each other. We can leverage this to create classes that follow the informal duck type matching rules. I want to look at applying the Liskov substitution principle in the cases where the subclasses do not match the superclass very well. Sometimes it's necessary to rethink the design to better align the subclass-superclass relationship, and in other cases it can help to apply the interface segregation principle and refactor the definitions. A document in Markdown format can contain tables of values. A table is very much like a CSV document. It has columns and rows. However, a Markdown document may be a whole chapter of a book, which means there may be more than one table. This means the read method needs a parameter to select a specific table from a larger Markdown document. But if we try to introduce an additional parameter to the read method, we can create a Liskov substitution problem. It looks like this. Here's an example of trying to introduce a new table index parameter to the read method. We get a warning from MyPy telling us that the signature of our subclass read method is incompatible with the superclass reader. MyPy calls it a super type, but I've been calling them superclasses. The problem, however, is the same. The subclass doesn't match the superclass. There are two common strategies for dealing with classes that aren't directly substitutable, but seems like they should be. One choice is to rethink the collaboration. Is the distinction really necessary? Does the design really require this parameter? The other choice is to refactor the design. Perhaps the new method can be pushed up the class hierarchy into a superclass. This would restore Liskov substitution. In this specific example, the table index isn't optional for Markdown. It doesn't really make sense to push this up into the superclass because the table index doesn't apply to file formats like CSV or JSON. A third approach is to add features by expanding the interface. Python gives us a number of alternatives. I can define additional methods to set the additional values required by an odd or unusual subclass. This is sometimes called a fluent interface. An alternative is to add parameters that have default values, making them optional for classes that don't need them. The default parameter path is so common in Python, a lot of people think of it first. My preference, however, is to compare both approaches. Sometimes we want what is called a fluent interface. In this kind of design, a number of methods are used instead of a number of parameters to methods. Python offers so many flexible ways to provide optional arguments that a fluent-style interface with a lot of methods isn't typical, but using this additional table index method allows us to preserve most of the main function without significant ripple effects. We'll still have a special case for Markdown, but none of the other reader classes or subclasses change. Here's the small change required to the main function. In the case where we're parsing a Markdown file with a suffix of MD, we've added the table index method to provide the needed additional value to the parser. Other than invoking this new method, the rest of the processing for Markdown version of the reader class is identical to the non-Markdown readers and to the superclass. The other common approach available in Python is to provide default values for parameters, making them optional. This leads to properly polymorphic classes. Here is how I can make the table index parameter to read optional. I provide a default value of 0. I think it's a good idea to use keyword-only parameters to support polymorphism. The asterisk here tells Python that all the following parameters must have values provided with an explicit name. So the code in the box shows how this is used by the main function with a keyword table index equals 1. That parameter name would be now required because of the asterisk in the function definition. No language can ever confirm that the subclass semantics match the superclass. It's entirely possible for a subclass to override a superclass method with an implementation that's simply bonkers. Unit tests are required to show that Liskov substitution truly holds. The Liskov substitution principle doesn't solve the problem of creating properly polymorphic peer classes. It provides a way, however, to articulate the concern. There are two common approaches to Liskov substitution problems: rethink or refactor. Subclasses should properly extend the superclass. If a subclass introduces a new feature incompatible with the superclass, that's very likely going to be a problem. The core value of Liskov substitution is to assure that the subclass designs match the superclass expectations. In some cases, the design may need to be refactored or rethought to align subclass and superclass. Generally, the isInstance function should be used rarely, if at all. When creating classes for which Liskov substitution works properly, there should never be a need to identify the type of an object. Since nothing is absolute, I don't really mean never, I mean almost never for an extremely narrow band of almost. This is something I see once in a while. We rarely need to test types like this with a check for a specific type. First of all, this breaks ordinary duck typing. A class that also implements the reader protocol but is not a direct subclass of reader can't be used here. Second, it's much easier to include type annotation and then turn tools like MyPy loose on the code to check those annotations. Here's the same code with type annotations. You'll notice I've used them in all the examples. The MyPy tool can check the code to be sure the readers and correlations are collaborating properly. In rare cases where a class needs isInstance to determine types is when writing coercion rules for Python's built-in types. We can't easily extend the built-in types, so we have to resort to using isInstance. This example code is a little contrived. It seems better to create proper builders and avoid all the explicit type checking. For classes we write, we can add methods or attributes to avoid this kind of isInstance type identification. The Liskov substitution principle looks at the signature of each class in a hierarchy. The signature is the collection of all the exposed methods and attributes. Are the signatures compatible? Does the subclass only add features via new methods? If so, then it's possible to replace the parent superclass with an object from the subclass. If the signatures are disjoint in some way, then substitution won't work, and this may mean that ripples of change will have destructive effects. When we're extending a class, we'll sometimes need to create subclasses that have extra features. In some cases, we can rethink the design and generalize the feature, making it part of the superclass. In other cases, we may have subclasses that don't exactly match the superclass. We can add methods and design a fluent interface. We may want to define a protocol to support duck typing. This can avoid a too simple check of the class hierarchy, and in many cases, we can add optional parameters to methods. The Python language offers no explicit support for checking types at runtime. Instead, we rely on tools like MyPy to do a deep analysis of our code and our type annotations. Even with tools like MyPy, there's no way to locate spelling mistakes. Unit tests are also required to be sure the subclasses work correctly. The Liskov substitution principle helps manage the subclass-superclass relationship. When a subclass can be used anywhere the superclass is used, the design will fit this principle. A class should be able to be replaced without a damaging ripple effect that causes other problems in the application.